something which I always enjoy talking with the students. So today I'm going to basically introduce uh, a software called SageMath. And since all of you are learning differential equation this semester, we'll look at how differential equations can be used to solve, how SageMath can be used to solve differential equations. But SageMath is much more than just solving differential equations. I believe last semester you all have had lab course in MATLAB. So, but MATLAB is a proprietary software, right? You have to buy that software. Of course, the VIT has procured that campus license, so that's why you people are able to use. But if you want to use it, you need to buy them. Whereas SageMath is free and open source software. I'll talk more on that. But before that, let me just very briefly tell you differential equation, why should one use, and some basic stuff. Then we will move on to introducing SageMath, and followed by using SageMath for solving differential equations. You can also use SageMath to kind of find Laplace transforms, Fourier series, and all these things. So I'll also tell you a little bit about that as well. Of course, on the way, I will also tell you how to use this, and maybe I will some of the codes I will share in the chat, and you can execute them online. I'll tell you the website through which you can execute. But more importantly, at any stage, if you have some question, or if I am asking questions, I do expect an answer, at least from some of you. And yeah, so please interrupt me if things are not clear. Okay. Okay. So let us go ahead. So as you know, differential equation is actually very, very important subject, especially in physics, engineering, and any technology, right? Basically, it is used for modeling a lot of systems. Whenever you want to model some system, differential equation is very, very important. And even in uh, computer science engineering, which all of you are doing, differential equation is quite useful. So I have just listed some applications which directly can be uh, can be uh, looked at in terms of computer science and engineering. But since all of you wish to be a computer science engineer, and your job is also to design software or design mathematical tools, so unless you understand differential equations on solving the algorithms, etc., you cannot design. So, right. So it is very, very important to understand these algorithms. Solving is one part, but understanding it becomes very, very important, especially if you want to design any software or kind of improve software, its efficiency and other things, etc. Okay, so some of the applications that one can directly see from computer science, like computer graphics and animations. Many times these differential equations can be used to simulate motions, deformations, and many physical dynamics of physical bodies. Like, for example, you all must have studied Newton's law of cooling. So that's nothing but a simple differential equation. You must have seen already this, how to solve using this. And similarly, in robotics or control system, a differential equation can be used, especially when you want to design algorithms for robotic arms and automatic vehicles, etc. All these differential equations is very, very important. Similarly, computational fluid dynamics, that's actually a branch of mathematics as well as a branch of uh, several engineering, where this computational fluid dynamics is taught or is learned. And for example, all these uh, flight simulations, etc., this computational fluid dynamics is heavily used. And computational fluid dynamics involves lots of differential equations, lots of, including partial differential equations, which I think also you have learned. Also, there is a whole new branch of neural ODEs. Now, neural network is very important. I'm sure all of you are using Chat GPT and all these things day in day out, right? So Chat GPT works on what is called the neural network, right? And there also they are looking for what is called neural ODEs. Similarly, if you want to train neural networks, there also something which gradient flow, etc., is very important. Similarly, if you want to do, let's say, edge detection or smoothing, partial differential equations are used, or noise detection. So all these edge detection, noise detection, smoothing, etc., these are part of image processing. I'm sure at some stage you are going to study image processing in your course, and you will see that some of these differential equations is used. Even in cryptography or network security or chaos theory, there also you come across several differential equations. Even you want to, let us say, model system or network modeling, spread of, for example, malware, that can be modeled using differential equations. Even in theoretical computer science, like automata or formal language, this differential equation are used. So these are some applications I have listed, but there are many applications of differential equations. I'm sure since you started learning differential equations, you must have already seen several applications, and how when you create any model, differential equation comes into picture, right? So let me look at one example, which is a kind of linear first order ODE, and that when you want to use, let us say, CPU cooling in a computing CPU, because it generates a lot of heat. So you need to and especially if you have servers, etc., it has to run continuously. So it requires cooling, right? So you can use differential equation. For example, many of these servers, they are kind of are placed in some of the area where the temperature is very low, so that they can save energy and all that, etc. If that, right? So it is very important. So for example, if you look at uh, this is actually uses just Newton's law of cooling. So if I look at capital T, temperature of CPU at time t, and there will be environment temperature, like temperature of the room temperature, right? That's T environment, you can denote it by, and K is, let us say, cooling rate, or it's a constant. So one can very easily model this like d capital T by dt is equal to K times T minus T environment. I'm sorry, you must have seen this. And T at 0 is 0, right? So this is a first order linear ODE with initial condition. Initial condition is T at 0 is T0. So T0, that is a starting temperature of the, let us say, CPU, right? So, and if you very easily, you can solve this using separation of variable, and the solution comes as T at any time T is T environment temperature plus T naught minus T environment, whole thing multiplied by T to power KT. So that's very simple. I'm sure you must have solved this many times. But so this is a simple first order ODE with initial condition. If you don't have this initial condition, this will call that a ODE. It may have multiple solutions, but once you have T0, initial condition is given, this will have unique solution. Now, of course, why it will have solutions, etc., that is also very important. I'll come to that. So in general, if you want to define first order ODE, then this is how you define dy by dx is equal to f of xy. So f of xy, that's a function of two variables, x and y. Here x depends upon y. So x is independent variable, y is dependent variable, and that's why you on the left hand side you see dy by dx. So dy by dx. So and solution of this is nothing but a function y of x which satisfy this equation. That's the solution, right? And in order to have this solution, you need certain condition on fxy, right? So one thing that required is, first of all, fxy should be continuous in both x and y, and you need extra condition also. So let me just give that extra condition. I'm sure you must have seen that. So these are all a repetition. So another extra condition that you need is called Lipschitz condition. That is simply that what simply means that if you take partial derivative of f with respect to y, then it should be continuous in some neighborhood of x naught. Simply, or you can think of this as it is bounded actually. Partial derivative of f with respect to y is bounded. That's another way of looking at this Lipschitz condition. So once you have these two conditions, then one can show that this differential equation has a solution, and not only that, it has a unique solution. So that is why it is called necessary and sufficient condition for existence and uniqueness of this solution. Now, it is very, very important to understand the initial conditions, setting up initial conditions, and also looking at whether the solution exists. I'll give you an example why it is important, because without that there could be some kind of drastic change in the output with a small change in time and all that things. We look at that. Okay, so but for example, if you look at this differential equation, dy by dx is equal to 1 upon y, where y0 is equal to 0. Now 1 upon y, y0 is given to be 0. So if you need continuity of fxy at 0, but you know that 1 upon y is not continuous in y, right? So this differential equation does not satisfy necessary and sufficient condition. And this, in fact, 1 upon y, if you take partial derivative of this with respect to y, this will become unbounded. So this will not have a solution. Similarly, you can look at, for example, dy by dx is equal to y to the power 2 by 3, and y0 at 0. This differential equation also, this right hand side, does not satisfy Lipschitz condition, though the first condition is satisfied. For example, y to the power 2 by 3 on non-negative y, this is continuous, but it does not satisfy Lipschitz condition, that partial derivative is not bounded. Partial derivative with respect to y is not bounded. So again, so for example, if you look at another equation, let us say dy by dx is equal to square root of mod y. Again, you can very easily check that this has two solutions. One is x equal to 0, trivially 0 everywhere. Another one is x is equal to x squared by 4. So these are two solutions, and that's because this function fxy does not satisfy the second condition, that is, it is Lipschitz. So in order to have solutions, you require those two conditions, right? So for example, let me just give you another example or model that, again, something similar you must have come across. So for example, we always have population, let us say, migration from one place to another place. So for example, let us say, just consider two regions or two cities, A and B, and from where people migrate from A to B and vice versa. So we can think of the population at time t as small a axt, and at time b, this will be proportional to axt. So a and b are constant, and migration rate from b to a is b, and the population at time t is, let us say, of b is yt. Then you can model this by this dx by dt is equal to minus ax plus by, minus ax because the population will go away from the city A, and whereas population from B will come to A. That is why here minus ax plus by. Similarly, the other one. So this is a system of first order ODE, and in fact, very easily you can convert this system into second order ODE, which is I have listed here. Very easily, you can just take the second derivative of x with respect to t. Right hand side you will come x or dy by dt, but that you replace it from the second equation. So this is, so not only you can convert this equation into second order ODE, but if you have a second order ODE, you must have seen that can be converted into system of first order ODE. Now, as a result, what happens if I want to solve second order ODE? Then it is good enough if I know how to solve system of first order ODE. So that is where solving first order ODE is very, very important. That is the most crucial. Because many times, even you must have seen, even you want to solve partial order differential equation PDE, that also it will actually get transformed into first order, and then you solve that. So it is the most important part is understanding how to solve first order ODE. And that is where you have several methods depending upon the nature of the differential equation. You have several methods. Okay. Now, so for example, if I can have some initial condition, and that also we can convert into second order ODE, right? Or even in, let us say, this is a famous model called SIR model, which is model for epidemic, right? In epidemic, you have susceptibility, you have infection, and you have rate of recovery. So if RT is number of people who have recovered at time T, ST is number of people who are susceptible to T, and IT is infected, number of people who are infected with certain disease. Now, for example, during COVID time, these models were very, very heavily used. So here you can see this model using these three equations, but you can have many more parameters as well. And this is, it depends upon, first one is minus beta times SI. So this is non-linear term. So this is system of non-linear ODE. So that I'm not sure whether you have solved such a system, but it is not easy in case you have a non-linear system to solve. So that is where we actually look at approximate solution. Many times as an engineer, even if you are not able to find exact solution, you are happy with something which is approximate or something which works, right? But even there, it is very important to understand the initial conditions and the other parameters which you are setting. It is very, very important. Okay, so very easily you can also actually find out necessary and sufficient condition for second order ODE, right? So second order ODE, how do you write? You can write this as dy. So y is a very, again, dependent variable, depends upon x. So dy by dx square can be written as function of x, y, and y dash, right? So something here, for example, which we have seen, d2x by dt square equal to, you can put everything on the right hand side. So fx t x dash is the negative of 1 minus 3 dx by dt minus 0.24 x, right? So here the necessary and sufficient condition for that is going to be, of course, it should be continuous in all the variables x, y, and y dash, and the first order partial derivative of f with respect to y as well as with respect to y dash. Y dash becomes another variable you can think of. That should be Lipschitz, right? So that should be bounded, right? So this is, and you can extend this condition to nth order ODE, right? So as I mentioned, these assumptions plus these conditions, satisfying these conditions are very, very important. especially if you want to design any system, which is a physical system, which is going to be used, it is very, very important. For example, you can look at, I just mentioned this here, there is a Tacoma Narrow Bridge, which in US, I think a Pageant Sound, which was opened in 1940. It is a suspension bridge, and it collapsed within 4 months. Actually, 1st July 1940, it was opened for public, and 7th November, it just collapsed because this of course it uses ODE, it uses second order ODE in this modeling, but then it got collapsed. Therefore, there are various reasons. One of the reason is also they did not look at the initial conditions, etc. properly. So that is, so it can have catastrophic effect, right? So it is very important to understand. It is not just you somehow you get the solution. That is just one part, but it is very, very important. And definitely, as an engineer, you are going to design many systems, etc. It is very important to understand what are your assumptions for the stability of the system. Okay, so you can I'll just put this in chat. You can look at, there is a video also for this. You can look at, actually they have recorded video how it collapsed. Okay, so of course that's unfortunate, but you can see here. So even if a lot of bridges and other things, etc., if it is designed, one has to look at all these things as an engineer, right? So so this was very brief introduction. I think somebody is annotating in my screen, so please remove those annotations. So it is very important to understand when you are setting up the system, the conditions for existence and the solution, and also the initial conditions. Okay. Now, with this introduction, let me move on to how we can solve this using Sage and what is Sage all about. Okay. So if you have any questions so far with this very basic introduction, you can unmute and ask if you have any question. So I have not told you how to solve any of these equations because you have already learned. But I just wanted to mention necessary and sufficient condition and why it is important with this example. But there are several examples of this kind. Okay, if not, let us go ahead. So we will look at what is SageMath. So let me just, is my second screen also visible? Hello? Can you see my second screen of SageMath website?
Yes, sir.
Okay. Yes, so I have just opened this SageMath website. Let me also put it in the chat, this website. So all of you can open in your system. So this is a open source, as you can see here. SageMath is open source mathematical software licensed under GPL, General Public License, and it is built over many open source software. It uses actually the NumPy, SciPy, Matplotlib, SymPy, etc. All these things you have learned in the previous semester in your Python course, right? So this is actually this is also what is called a computer algebra system. So when I say computer algebra system, what does it mean? You have seen MATLAB last semester, all of you have used. That MATLAB is also a computer algebra system. So in MATLAB, what are the things that you can do? Of course, you can do numerical computations. You can do visualization in terms of plotting, animations, and all that. Then you can also do symbolic manipulations. So in MATLAB, you can also define symbols, symbolic variables. and do computation. You must have already seen. You can find directly derivatives, integrals, and all that things, etc. And the fourth thing that you can do in MATLAB, you can also write your own program, right? So these are the four things you can do in this software. So any software, mathematical software in which you can do all these four things, namely numerical computations, symbolic manipulations, which in mathematics is very, very important, in other science also, then visualization and programming is called computer algebra system. So SageMath is one such computer algebra system, which was designed by one of the mathematics professor from Washington State University. And he designed this, his mission of designing this was to create a viable free open source alternative to Magma, Maple, Mathematica, and MATLAB. So these are all proprietary software, paisa wala software, right? You need to buy, you need to pay a lot of money in order to buy. For example, single Mathematica license will cost you at about 1.5 lakh rupees. Even MATLAB will be of same order, right? So his aim was to create this. But then when we started creating this, lot of already free softwares were already available. So instead of creating everything new, he created this as a platform, and he used all these software maxima, which is again a computer algebra system, along with Python, etc. Now, as I said, in MATLAB, the programming you write in MATLAB is different from programming in C or programming in Python, right? Of course, you can run Python program from MATLAB also, but the writing program in MATLAB is different. So it has its own programming language. So instead of creating its own programming language, he thought of just using Python. So SageMath is built on Python. So all of you know Python, so it is very easy to kind of use this. You do not need to learn another language, and it is free and open source. Free, all of you understand, right? Open source means you can not only use it freely, but you can see the source code. In MATLAB, you cannot see the source code. Not only you can see the source code, how the program is written, but you can modify in your system. And not just that, you can go one step ahead. You can even share with your friends, with your colleagues, right? So that is called open source software. So SageMath is one such. Okay. So, and of course there are some. This is how you can install SageMath. Current version is 10.6. But only thing is, in case you are using Windows, you may have to install using what is called WSL, Windows subsystem of Linux, right? Till 9.5, they used to have Windows executable file, but they don't have. If you're using Linux or Mac, you can directly install. But for Windows, you need to install through WSL. But you can also use online. So for example, if I click on SageMath cell, if I click on this is where you can type everything. You can type everything, all these codes. So let me also put this this code in chat box, this link. So you can open this, and this is where you can type anything. For example, if I want to add two numbers, I can simply say, let us say this number plus another number and evaluate. Immediately I will see the output. You can see the output. And all these things, everything that you can do in installed version of Sage, you can also do it here. So along with me, some of the codes, I will just put it in chat message. You can even execute it here. Okay, so let me get back to this file. So now let us look at very briefly how we can make use of this. So let us define a number n, which I have written as 98. N is equal to 987654321. starting from 9 to 1 in decreasing order. Now, so if I this is a number, if I ask you what do you know about this number, and or if you want to know more about this number, then what are the questions that will come to your mind? For example, very easily, since it ends with 1, it is an odd number. Apart from that, what can you say, or what are the things that you would like to know about this number? Any answer? Any
The
answer?
data type, sir.
Data type. Okay. Since you have learned programming, that is one question. Yes. What else? What else you would like to know about this number? So data type, let us say this is going to be integer data type. What else? Numbers we have been learning from first standard itself, right? So you know a lot of things about the numbers.
So whether it's a prime number or not.
Whether it is a prime number or not, very good. Anything else? If it is a prime number, we can't do much. But if it is not a prime number, what are the things that we can ask? What are the factors?
Yes, sir.
Right? All these things. So a lot of things that we can ask. Okay. So I have executed this number, and actually, so here you have, since you have learned Python, in Python, when we put it like this, actually it thinks of as an object, right? Python is an object-oriented programming language. So here n is an object, and you want to apply any methods which are available on that object. What do? You use that object dot, right? Dot operator. So here also you can do n. If I say n dot and press tab, it will give me whole lot of options. These are the methods which can be applied. So in principle, I don't need to remember any of these commands. I can just look at this tab, and then it will give me the option. So for example, somebody said we want to know what is data type of this. So if I say n dot parent, it is says it is coming from integer. It is integer ring. So it thinks of as a ring. Ring is a kind of some kind of mathematical concept, right? So that is what it says. The parent is ring. So that's a data type, right? Many other things. For example, you say n dot number. Let us say n dot. If I say b, so for example, they can say bits, n dot bits. Now it will give me all the bits 1 0 0 0 and so on, right? You can even find out number of bits. So n dot n bits, right? So so it tells me. Let me also copy this fellow. So it tells me it has 30 bits, right? Number of bits in this integer is 30, right? So for example, we can even find out how many digits, n digits, right? Though I'm typing it here, but this has 9 digits, right? So very easily you can find out all these things. Somebody said whether it is a prime number. So if I say n dot is underscore prime, is underscore prime. So that is how the method is defined here. Is stands for you're asking question, right? And then prime. So it says that it is not a prime number. This is not a prime number. Okay. If it is not a prime number, you would like to know what are the factors. So I can say n dot factor. I can say n dot factor. So this says that this has 3 square, 17 square, and 379721. Okay, these are the factors. Okay, if it is not a prime number, you can even find out. You can find out a number which is just bigger than this and prime. So you can say n dot next underscore prime. N dot next prime. Okay. So and similarly, you can find out next previous prime. So if I'm looking for a prime number, near to this, then very easily we can find out. Similarly, you can So all these, sorry, all these methods you can very easily apply, right? Of course, there are functions also that can be applied on F, right? But these are the methods because it created N as an object, and all the methods that you can apply, you can simply access that using dot tab. The same thing you must have seen in Python programming. You have already learned, I think, classes, Python classes. So all these concepts you must have seen, right? So let me ask you a simple question. So for example, you saw that this number is not a prime. How about if I, let us say, permute these numbers, is it going to be a prime? Let me include one more digits. Let us say 0 also. So we have 10 digits, right? These are the only digits. All numbers are made out of digits 0 to 9. So let us ask, can we find, is there a prime number consisting, having 10 digits, right? Consisting of all digits. Is the question clear? Is there a prime number having 10 digits in which each digit 0 to 9 appears? That's the question. Now, very easily you can write Python program for this. You will get. But here we can also combine power of. So, for example, I wrote this program. Okay. So what I'm doing here, I'm importing from iter tools. I'm importing what is called permutation. So permutation will give me all the permutations of whatever list you have. Okay. So I have created a string with digits 0 to 9, and this we can create permutation of all these things using this import. And then we are looking at take each of these permutation, and in case p of 0 is 0, that means the first digit is 0, then it will become only 9-digit number. So I'm skipping that, then continue. Otherwise, you join all these things, so make a number and check whether it is a prime number. Already you saw that this function. And then if it is prime, return, otherwise. So this is a simple Python program, right? Let me run this. First, let me copy this in the chat. And if I run this, then it is telling me, what is the answer I'm getting? 10 digit, there is no prime. So you see that? There is no prime having 10 digits in which all these digits appear. Okay. So here we have combined power of Python and SageMath, right? So this otherwise you could have written program for this very easily. Okay. And you can see here, this is just a simple Python program, right? So if you have learned Python very easily, you can learn SageMath, right? So and if I ask about the same, for example, instead of 10 digit, if I say 9 digit only, right? Though I'll keep the function name the same. Then let us see whether it is uh, going to give. I have excluded 0. This also there is no prime of 9 digits. Okay, so you can see here. Of course, here it means that we are taking the numbers digit colon colon minus 1. It means that we are writing in reverse order. First we are starting with 9, 8, 7, 1 up to 1, and that is what we already saw. It is not a prime. Okay. Similarly, you can find factorial of a number. So if I say, let us say n is equal to 2025, right? That's the year in which we are all in, and I can find out what factorial of this number. So factorial n. If I say factorial n, I have not executed this. Now let me execute this. Okay. And then when I say factorial n, you can very easily. So you can see here, it has a huge number of digits, right? Huge number of digits. Okay. And you can even count how many digits are there. So factorial n digits, and then you can count even how many zeros are there. very easily I could have counted. So I can say factorial capital N, and we already saw a function called n digits, number of digits, right? So this has 5819 digits. Factorial 2025 has this many digits. And you can even count how many zeros are there. There are 1025 zeros, not just trailing zero. These are called trailing zeros, but all the zeros in between, etc. There are 1025. I can ask a simple question, right? For example, write a Python program to find number of trailing zeros in n factorial. How many zeros are there, right? How many zeros appear? For example, if I write 5 factorial, it will be 1 0. If I write 10 factorial, how many zeros will be there? You can very easily find out. So for example, this is a program. Actually, you can keep on dividing by 5. So as many division by 5, that will give you number of trailing zeros. This is a Python program. And if I run this, then it is telling me there are 505 zeros which are at the end, right? Let me also put it in the chat message, right? So you can see here, I'm not using any, right? Only I'm writing Python program and it is running as it is. So we don't need to learn separate programming language in order to use SageMath. Okay, that's the beauty of this. Similarly, let us say you must have already seen what is Fibonacci sequence, right? You must have written program also. So Fibonacci sequence is a sequence whose first digit is 0, sometimes also starts at 1, second is 1, then so first 2 you have, and then next one can be defined as sum of the previous 2. Okay, in fact, SageMath has inbuilt function to find factorial. So for example, if I look at nth Fibonacci number, so if I look at Fibonacci 10, that's a 55. So let me ask, what is Fibonacci 0? It starts with 0. So that is how it is defined. Fibonacci 1, this is 1, right? And I can list Fibonacci sequence 10. So it will give me all the Fibonacci numbers up to 10, first 10 Fibonacci numbers. Okay, similarly, you can, so right, so you can look at some, let us look at some one or two facts about Fibonacci sequence. Fibonacci sequence, by the way, is very important sequence. It appears in nature very frequently. You can look at what are applications of Fibonacci sequence in nature. So for example, one of the property is that summation fk, k going from 0 to 1. That means if you add all the first n Fibonacci number, that is nothing but n plus 2 minus 1. That very easily you can prove. Or if you take the square of each Fibonacci number and then add from 1 to n, 0 is 0 only, so it doesn't make any sense, doesn't make difference. This is nothing but product of fn and fn plus 1. Okay, so let us just try to verify this. How we are going to verify this? Let us verify this for 100. So what we are going to do, we are generating kth Fibonacci number for k in range n plus 1, and then making this list. And once we have made this list, then I'm taking the sum. So this is a list comprehension, right? This is what you must have learned in Python. And so left hand side is sum of first kth Fibonacci number and that equal to. So I'm checking whether these two are equal, is equal to fn plus 2 minus 1. And when I run this, it tells me it is true, right? And this I can do it with any n. So even if I put, for example, let us say put 200, it may take slightly more time, but it will work. If I put 500, still it is working. If you take n very large, it will take more time, but it will work. Similarly, this is the first verification of the first property. If I want to verify the second property, right? What was the second property? Take the sum of the squares of the n Fibonacci number. So again, I'm using the same thing, sum of the squares of n, and is it equal to fn into fn plus 1? And the answer, of course, I will get should be true. So let me first copy this for you. And if I run this, then it says true. So very easily, we can verify some of these properties. There are several other properties of Fibonacci sequence. You can even look at, if you look at, for example, the limit of fn plus 1 divided by fn. That's a sequence, and that sequence actually converges, and it converges to, does anybody know? If I write, for example, this, let me say limit as n goes to infinity of, I'm just writing something, don't worry about this. This is what is called LaTeX code. Yeah, so limit of fn plus 1 divided by fn. This limit exists. Does anybody know what is this limit? Any of you? Okay, this is what is called golden ratio. So this converges to some number which is called golden ratio. And golden ratio is very, very frequent in nature. Lot of stability in nature is because of this golden ratio, is attributed to this golden ratio. In our body also, golden ratio, the Fibonacci sequence is there actually. If you look at, for example, I don't know whether you can see, if you look at the finger length, this length followed by this, and then this, so on, that follows Fibonacci sequence, right? So this golden ratio is defined in Sage. So for example, you can define what is pi, value of pi, right? Similarly, you can define what is golden ratio. Golden ratio. Let me find the numerical value of this. This is 1.6180 and so on. You can look at what are the applications of golden ratio in nature. You will come across several. Okay, next, let us look at, you have also learned calculus in your previous semester, right? And both including first variable and multivariable calculus. So all these things can be very easily explored in SageMath. Of course, I know that you also had a MATLAB, SageMath, calculus lab using MATLAB, but all those things which you have done in MATLAB can be done in SageMath. So for example, let us define a function called fx is equal to sine 2x plus exponential of minus x plus x squared. Okay. And again, so this is how you can define a function of one variable. We copy this function of one variable. And anything that you want to find out about f, so here f created an object. So again, you can say f dot and press tab.
In the past 19 classes. Oh.
Hello. Yeah. Can you mute yourself if you're not asking questions? If you have question, you can unmute and ask. Okay. So as I said, here f is an object, and anything that we want to find out about this object, I can simply say f dot and press tab. All these things will appear. Right. So anything that you want to do with f can be found here. Right. So we will come to this, but let us first try to plot graph of this function. Let us plot graph of this function. This is how the function graph looks like. And what is it? F dot plot -3 to 3, color is equal to red. So it is plotting graph of this function red in color. Let me reduce the figure size, I'll say fig size is equal to, let us say, maybe 4. Okay, this is how it looks like. Of course, by looking at this figure, you can find out whether it is continuous, whether it is differentiable, and all these things, etc. Right? We will look at some of it quickly. So, for example, let us define a piecewise function. Lot of functions you must have dealt with while learning Fourier series of this nature, piecewise function. So let us define this function. This is how we can define. So here I am declaring x as a variable, but you need not x always thinks of as a function. X always thinks of as a variable. And let me plot graph of this function. So p f dot, I call this function as f underscore piecewise. Sometimes it takes time when you have to define piecewise, because it has to at the corner. But so let us just wait for this. In the meantime, let me copy this also. So this is a piecewise function. I think I need not have run this. Let me, I can interrupt the kernel. Okay. I'm sure all of you know how the graph looks like. But if you look at the graph of this function, this is how it looks like. The blue curve is the graph of this function. And this actually, it lies between minus x square and plus x square. So that is what we have drawn. I've drawn these two graph of x square and minus x square, and I have plotted this. I have plotted this along with the other two graphs. So, and I'm sure you must have come across these functions, right? So what is the function here? The function is how it is defined. It is defined as x square into sine 1 by x, and at 0 it is defined as 0. So if you look at this graph of this function, what can you say about this function? Is it continuous at 0? Is it continuous at 0?
Yes, sir.
Yes. Is it differentiable at 0? How do you check that?
Yes, sir.
Is the derivative continuous? Yeah. So
It
all these
seems
things you can find out. Yes, yes. All these things you can find out very easily. Yeah.
Sir, it is
go
a
ahead.
parabolic function. So, sir, it is a parabolic function, so it will be differentiable at
No, I'm talking about
all the points.
I'm talking about the blue one, not the red one, which is x square and minus x square. Right? The function that I'm talking about is this. F of x is equal to x square into sine 1 by x. So here you can even find out even the left hand limit at 0. So let me, this again you must have seen how we can do it in MATLAB. Similarly, I can find out right hand limit. So here that left hand limit is direction is equal to in the single quote you write minus, and right hand limit for you write direction is equal to plus, and the function for the limit is just okay. So left hand limit, right hand limit, both you can find out very easy. Okay, so here both left hand limit is same as right hand limit, and we can also find out the limit. If I don't say any direction, it will give me the limit. right? So, and that is what you saw here. This blue graph, that is actually a graph of continuous function. This is a continuous function. Of course, it varies quite fast near 0, right? But it is continuous. You can even check whether derivative is continuous. So for example, let me define that as an expression. I can define with not as a piecewise function, but I have just declared x square into sine 1 by x in f underscore expr, and we can find out derivative of this. We can find out derivative of this. So that's the derivative, right? So let me copy this. Or we could have simply, instead of finding calling this function diff, I could have simply said f dot expr, right? Sorry, f underscore x is the name, and then dot diff. This will give me derivative of the function. Instead of diff, if I ask for 2 here, if I put, it will give me second derivative. If I put 3, it will give me third derivative. So all these things can be very easily obtained. And another beauty of this is that no matter what kind of function we have, the concept, for example, the limit of one variable function is obtained using limit function. Even if I have two variable function, limit, again it will be obtained by limit function. Derivative also, diff or differentiate also there. Okay, right. For example, we can even find out this derivative using first principle. Limit of this minus f at 0, which is defined at 0, divided by t is going to 0. So that, but here t I have to declare as a variable. Okay, so therefore this we are able to check derivative of this using first principle. Okay, you can very easily plot the derivative, right? Now you can see here what is happening with the derivative. Okay, it is varying very fast near origin. So whether it will be derivative, whether it is going to be differentiable, continuous, etc., all these things you can find. Or let us even you can find its you can find its integral, right? So for example, let us look at this function. F of x, g of x is equal to cos x into exponential of x square plus x into sine 3x. Okay, and we can plot graph of this function. So this also, let me copy, and we can plot graph of this function. This is how it looks like. Okay, of course you can find out derivative of this function. You can find out second derivative. You can find out 10th derivative, right? Of course, these are all very easy, right? You can even find out Taylor series expansion. So g dot Taylor with respect to x at 0, about 0, and of degree 5. This is a 10th degree, 5th degree Taylor's polynomial. Taylor's polynomial is one of the most powerful tool as far as approximation is concerned. All the numerical value that we find in our calculator or in computer, etc., they are based on Taylor series expansion, Taylor series approximation. Okay, so this, you saw that this is a function, right? This is how it looks like. So for example, if I try to revolve this, if I want to find out surface of revolution of this about x-axis, how will it look like? That you can also do here. So let me just show you that. Let me show you that. I'll just copy this fellow first for you. So if I look at this, let me run this. Yeah, can you see the graph? This is surface of revolution of this curve about x-axis. Okay, right? Of course, similar thing is there in MATLAB. So how the function is defined? Revolution underscore plot 3D of gx, x between -3 and 3. I'm also showing the curve, and opacity is equal to 0.7. So it's some kind of transparency, right? Aspect ratio is 1, 1, 1, right? This is how the graph looks like. So there is a whole small hole it looks like, because at 0 is right. So that's because of the plotting. Really, there is no discontinuity at 0. Okay, right? So, and you can even find the surface integral. So the surface integral of this is how it looks like. But if I look at this function and try to find out derivative of this underscore 1 plus f dash x whole square, etc., I'll show you this. This is how it looks like. The function is quite complicated. Finding integral of this will be next to impossible. So what you need to do is you have to find numerical integration, approximate integral. And there are many methods of doing that. For example, here there is an inbuilt function called numerical integral of this function, right? And the numerical integral is 64.78. So that is the surface area of the surface of revolution between -3 and 3, and rotated or revolved around x-axis, right? So where is the chart? Let me copy this. So not only you can find out integral symbolically, but you can also find the integral numerically, because not everything simple. If I say integral or integrate, both can be the integrate of, let us say, sine of 2 star x with respect to x, then it will give me. Or if I say integral of this with respect to 0 to, let us say, 1, then also it will find out, right? So it can find symbolical integral, but if the integral is not possible to find, then you can find numerical integral. Okay, you can also deal with function of more than one variable. So suppose first let us declare function of 2 variables. Okay, so first you need to declare x and y as variable, and let us say this is the function I have. hxy is equal to 5 into x square minus y square into x e to the power minus x square minus y square. Okay, so let us declare this function, and you can plot graph of this function. Okay, you can plot graph of this function. This is how the graph looks like. Let me again copy this for you. Okay, this is how the graph looks like. You can see here it looks very nice. And since already you have learned calculus, this is a very nice graph. It has 2 local minimum, 2 local maximum, and 1 saddle point, right? So all these things can be very easily obtained. So for example, you can find out gradient of this function. H dot gradient will give me gradient of this function. Similarly, I can find out Jacobian of this. All these things you have learned. You can find out Hessian of this. This also you have learned. Okay. Let me once again copy this for you. So this is how you find gradient. This is how you find Hessian, Jacobian, and this is how you can find the Hessian. Okay. And for example, if I want to find out Hessian at -1, 1, I can simply say h dot Hessian and x equal to -1, y equal to 1. It is this one, right? The cross term is 0. Yes. Any question, Manas? Okay. We can even plot contours. This is how the contours near zero look like. This is how it looks like. So these are the point of local maximum or local minimum. This is the saddle point. Okay. This is saddle point. You can even, let me copy this fellow also for you. Okay. Not just that. For example, I can plot these gradients. This is how the gradient looks like. So you can see here, this is one of the local maximum, local minima, where the arrows are converging. So it's a kind of sink. And from here, these are all going away. And at this place, something is going out, something is coming in. So that must be the saddle point, right? That's the geometric meaning of the gradient in terms of local maxima, local minima. Okay. So let us actually try to plot these vectors with unit length. So I have normalized this and then I have plotted. So all the arrows you can see here, it looks like of same length. And let us plot contours along with the vector field. Let us plot contours along with vector field. Okay. So now you can see here, this is how it looks like. So at this place, all the arrows are going inside. So that's a sink. At this place, all of them are going out. And at this place, you can see that something is coming in, something is going out. Both is. So that's a saddle point. These two may be, I don't know, let us just check, right? You can actually find out what happens, how does the gradient behave at the point of local maximum, local minimum. But another thing that you can notice is at every point, if I look at this curve and this arrow, they are orthogonal. So the gradient is orthogonal to that curve or the tangent to that curve. That is very easy to prove, but this is what geometric meaning is. Okay, you can even find out critical points of this. So I can simply say solve derivative of f with h with respect to x equal to 0 and derivative of h with respect to y equal to 0 with respect to x and y. Then it has, you can see here, it has 5 critical points: 0, 0, minus 1, 0, 0, 1, 0, 0, 1, and so on, right? And if I, for example, if I take any of these points, for example, if I take minus 1, 0, so this one I'm looking at, right? So if I find out Hessian at x equal to minus 1, y equal to 0, the Hessian is, this is negative here, this is positive, so the determinant is positive, whereas this term is negative, so it will be local minimum. It will be local minimum because Hessian is negative definite, right? Sorry, Hessian is negative definite, so it will be local maximum. I'm sorry about that. So at local maximum, you can see here what is happening with this gradient. They are all going inside. So it is a sink at this point. And at this stage, it will be local local minimum, that is positive depth. Okay, so all these things can be done. So all the concepts that you have learned, all the MATLAB, you have done lab in calculus, everything you can explore here as well. And this is free. Okay. Of course, there are some advantages and disadvantages of all these packages, but the alternative free things are there. Now let us move on to, if you have some questions, let me know. Otherwise, we'll try to explore some differential equation. Any question? Yes? Am I audible or no?
Yes, sir, you're audible.
Hello.
Yes, sir, you're audible.
Yeah. So
Yes, sir.
Okay. So let me go ahead if you don't have any question. Of course, this was just very basic introduction how some of the calculus can be done using SageMath. I wanted to tell you because you have already learned this using MATLAB. So I just why some of these concepts I know you have done. So, okay, now let us look at how we can solve differential equation using SageMath. So let us again come back to this first order ODE, dy by dx is equal to fxy. So when I look at this, so dy by dx, what does dy by dx represent? It represents a slope, right? It represents a slope. So it tells me that slope of the solution at xy has the value fxy. So for example, if I fxy equal to 0, that means the slope at every point is going to be 0. Now, which function has slope 0? Constant function, right? So solution of this is going to be constant, right? So very easily you can plot this. So for example, let us look at, suppose I have a differential equation dy by dx by dt is equal to 1, constant 1. I can plot the slope field of that. This is how it will look like. This is how it looks like. Slope field, right? This is constant 1. So everything is, so the solution of this is going to be, so dy by dx is equal to 1. So this will have a solution y equal to x. And that is what you can see here. Okay, let me copy this. So, okay, of course, I will share this worksheet also, but you can also plot the solution curve at every point using what is called streamline plot. So if I use this, now you can see here, along with each curve, there is a, along with each arrow, you can see here the solution curve. So for example, if I look at this fellow, this is the solution curve. And so initial condition, for example, x equal to 0, this will be the initial condition. And this is a curve. I can plot the single one also, but this is what is called slope field. And that is what is reflected. If I take another example, for example, now let us look at dx by dt is equal to 1 minus tx and try to plot the slope field along with the curve, along with this solution curve, also known as integral curve. So for example, if I look at this point, the solution is going to look like this. And also it is very evident, no solution curve will actually intersect. Okay, no solution intersect. So, and you can take any differential equation, first order ODE, and you can plot its solution, its slope field along with the solution curve, right? So here there is another example, dx by dt is equal to t square minus x square. This is how the solution and the slope field looks like. Okay. Okay. And there are many such. So this is for sin t into cos t, dx by dt is equal to sin t into cos t. This is another one, t square upon 1 minus t square minus x square. This is how it looks like. So you can see here there is some kind of bad behavior near 0, somewhat not very, it doesn't look that nice. Or you can look at, for example, if I look at, let us plot this. Now here, let me ask a question. So for example, here, what is my differential equation? The differential equation is dx by dt is equal to minus t by x. So very easily you can solve. But if you look at this, the solution curve, can you guess what should be the solution? What kind of the slope field you are getting? What are the solution curves here? What kind of solution curve you think is this? Yes. What was the differential equation? Dx by dt is equal to minus t by x. or maybe let us think of in terms of xy. So dy by dx is equal to minus y by x. That's the differential equation here. And I have shown you the slope field along with the streamline plot or the solution curve at every initial guess. And it looks like this kind of curve. So what kind of curves are these? Yeah, I want some answer. What kind of solution curves are these? Any of you? This is circles, no? Concentric circles. So that means the solution is going to be circle. So therefore, what is equation of a circle? X square plus y square is equal to a constant, right? So solution of this differential equation is going to be nothing but x square plus t square is equal to a constant. Okay. So many times by looking at this slope field, we can even guess what should be the solution without even going into the solution, without even solving actually. Right? So that actually gives you an idea about the solution. Okay. Or let us, for example, now look at this differential equation. Dy by dx is equal to x into, in the numerator, x into 1 minus x divided by y into 2 minus y. So very easily you can solve this. How will you solve this? What method will you use to solve this one? Yes. What method will you use to solve this differential equation?
Variable separation method, sir.
Variable separation method. Quite easy, right? You can write dy by dy into y into 2 minus y is equal to dx into x into 1 minus x. Right. So let us try to solve this using Sage. So first, again, let us first plot its slope field. First, let us plot its slope field. It looks complicated differential equation, which is not, but this is how the slope field looks like. Looks quite interesting. Okay. Now, if I solve this using Sage, so Sage has several inbuilt functions. One of them is called DE-solve. DE-solve. Okay. If I further, for example, if I put DE-solve and then tab, you can see several functions. DE-solve underscore Laplace. So it will solve using Laplace method. DE-solve min tides. It uses certain package. Then ODE int. Again, this is coming from Python SciPy. It also has some numerical methods of solving using RK4 method. You can also solve system of ODE and system of ODE using RK4 method. And there are other also. Right? So are you people also learning some numerical solution of the ODE? Have you learned some numerical solution of ODE? I think no, right? Dr. Divya, is that also part of the course?
No, sir. No, sir. No
Okay.
numerical.
So at present, only analytic solutions is done.
Analytical.
Okay, okay. So let us solve this. So how do we solve this? Of course, what you can do is you can look at DE-solve and how do you find help document in Python. You can just put question mark and then it will give you description, right? So it says that the function is DE-solve. You have to give the differential equation. What are the variables, initial conditions, and independent variables? This is a dependent variable. This is independent variable. What method you want to use, that you can actually show what is the method it is using, and so on, along with lots of examples. So these examples you can very easily directly you can copy and paste it in your so let us look at, let me get rid of this fellow. I'll comment this out. Okay, so if I say I'm defining this function, and then y is equal to function, define y as a function of x, and then declare this dE is equal to dIf derivative of f with respect to x double equal to fxy. Fxy is defined like this, and then say dE solve dE with a dependent variable y, and this is the solution. Of course, this is an integrating constant, right? But if I have initial value problem, for example, let us put initial condition y at x equal to 0, y at x 0 is equal to 1. So if I say this, instead of just using this, if I first, let me copy this so that in the chat. Okay, now if I say D is solved, initial condition I'm giving 0, a list 0, 1, that means x at 0 is equal to 1, then this is the solution. Now the constant has gone, that constant is 2 by 3. Okay, and very easily we can plot this. We can plot this very easily. How do I plot? So I have just declared this as an implicit plot. I have defined y at x is equal to another variable z, and if I plot this is how the plot looks like. You can see here. This is how the solution curve looks like. Right? Very nice curve. This is implicit. This is not a explicit function. Right? Right. Similarly, let us use another maybe condition. Suppose x at 0 is equal to 0.5, and let us solve this, and let us plot this one. Let us plot this one. Then you can see here the green one is the plot of the second solution. This is how it looks like, and you can see here these two are not intersecting. In fact, no two solution curve will intersect. Okay, very nice. So this is how you can, if you are using this kind of software, you can not only solve. Of course, it is very, very important to know how to solve analytically. And before that, as I told you, it is very important to know whether the solution exists and the initial conditions, etc. The parameter that you are setting is very, very important to understand. It is not just enough to solve, because these days we have lots of software to solve differential equations. So it is not that important. I mean, you can always solve, but it is very, very important as an engineer to understand these assumptions. Otherwise, it can be a catastrophe like Tacoma Bridge, right? Okay, so similarly, you can look at, for example, this is another first order ODE, dP by dt is equal to Rp into 1 minus P by K. This is known as population growth model. It's called logistic population growth model, where K is called carrying capacity. So the only that much population can survive, that is carrying capacity. R is the growth rate. R is the growth rate. Now we can solve this differential equation very easily. How do we solve this? So I'm declaring again T as a variable, P is a function of T, and R I'm taking as 3 by 100, and K is 1500. So this 1500 populations is carrying capacity. If I solve this, this is the solution. Now let me copy this. And so you can see here everywhere there is a multiple of 100 by 3. So a whole thing I will multiply by 3 by 100, and then we will simplify. We will simplify this. So then the solution looks like 3000 into e to the power 3 by 100 t divided by 2 into e to the power 3 by 100 t plus 13. Okay, that's how the solution looks like. And let us now actually find out the right hand side of this as a function of t. So this is how it looks like. And let us plot the solution. Let us plot the solution. This is how it looks like. Let me reduce the figure size. This is how it looks like. So you can see here, it started with 200, but the numbers are not shown here. And it is increasing. And after that, this is a y equal to 1500. At 1500, it is becoming close to 1500. So it is growing and it is becoming constant about around 1500, right? If I change the initial condition, for example, initial condition I put only instead of 2000, instead of 50, earlier it was 200. Initial condition was 200. That is what you can see here, 200, right? So from 200 it grows, right? If I put initial condition instead of 200, if I put, for example, 2000, if I put 2000, then how will the solution look like? Now you can see here, now it is coming down and becoming close to 2000. This is again y equal to 1500 only. So that is how will the graph look. Okay. So if you have more population, it will stabilize at 1500. If I make it 1000, that is carrying capacity, again the similar thing will happen. Okay, again the similar thing will happen. Okay, so that is how the solution looks like. So these kind of tools helps you to understand behavior of the solution. Okay. Similarly, you can look at this differential equation, y dash equal to 2xy equal to e to the power minus x square. Can somebody tell me what kind of differential equation is this? This is first order again. It is linear ODE, but it is non-homogeneous, right? This is not, right hand side is non-zero, so it's a non-homogeneous. If I want to solve this, very easily you can solve this using standard method like integrating factor. But here, if I want to solve this, this is how it looks like. C plus x into e to the power minus x square. That's the solution. Or if I want to solve it using initial condition, let us say x at 0 is equal to 1, then the solution is 1 plus x. So C has become 1 plus x into e to the power minus x square. That's how the solution looks. And of course, you can plot graph. But you can also solve second order ODE. For example, let us look at this function. 4 into d2y by dx square plus 4 dy by dx plus 17y is equal to 0. Y at 0 is 0 and y dash at 0 is 2. This is a homogeneous ODE. And if I want to solve this, how do I do that? Again, the same function d solve will work. And I'm here giving the differential equation d2y by dx square plus 4 into dy by dx plus 17y double equal to 0. And then when we solve, this is how it will look like. Okay, so it has two constants. I'm sure you know that why there are two constants. But if I have initial conditions, then I can just add 0, minus 1, 2. So y at 0 is minus 1 and y dash at 0 is 2. That's how the difference, the solution looks like. This is how the solution looks like. So same DE solve can solve first order. It can solve second order. If you solve higher order, it may be able to do, but not necessarily, because things may not be easy to calculate. That is why. But of course, we know that every higher order can be converted into system of first order, and then you can solve this. If I try to plot graph of this, this is how the solution looks like. Okay. And then you can, even if you have non-homogeneous system like y double dash equal to 4 minus y dash plus 4y is equal to 1 plus x e power x, that also you can solve using same way, right? So, but not always you can actually solve. For example, if I look at this differential equation, dy by dt is equal to t upon y minus t square y at 0 is 4. And if I try to solve this, Of course, this is a solution curve. Again, you can see here near 0, there is some not very good behavior. And when I try to solve this, of course, this you can solve very easily. This is how the solution looks like. Y is equal to square root of 16 minus ln of 1 minus t square. So there is a square root involved here. So if you solve here, you will get some imaginary term. Why that imaginary term? You can understand here. This is how it gives. Of course, so sometimes whatever solution that output you are getting from any software, etc., you also need to interpret. You should not just directly take the whatever output you are getting and then use it. It's very, very important to understand what kind of output you are getting. So for example, we can also solve numerically. So many times, if you have a differential equation whose analytic solution is difficult to find, you know that there is a solution exists, but it is difficult to find. Then we solve what is called numerical solutions. You are going to learn at some stage, but that is very, very important, especially for approximation and other things, etc. Because most often, when you are modeling the systems, etc., your differential equation will become very, very complicated with lots of parameters, few hundred parameters and things like that. So you cannot, it is just impossible to solve analytically, though the solution may exist. That again, I just told you, it is very important to know whether the solution exists. But once it exists, then actually solving is not easy analytically. So we need to solve numerically. One such solution, one such method is called RK4 method or Ranjit-Kutta method. This is how it works. I'm just giving you algorithm. Y at t plus h, right? So h is step length is equal to yt plus 1 upon 6 k1 plus 2 k2 plus 2 k3 plus k4, and where k1, k2, k3 are defined like this. This is for solving first order ODE, namely dy by dt is equal to sum f of yt. Okay, so let us look at, so for example, the same problem which we have looked at here, dy by dt is equal to t divided by y minus t squared 2. If I try to solve this numerically, if I want to solve this numerically, I think this is not the same one, y squared by 2t it is. So let us write this. This is how the solution looks like. You can see here the behavior. This is how it is going here. At 0, there is some kind of odd behavior. So if I and here it is using DE solve RK4 of F initial condition. So here let us give initial condition 0. What was the initial condition here? 0, 4. 4. Now that's the solution curve. At 4, this is how it looks like. If I say at 0, 0, which is fine. At 0, 0, now you can see here there is some kind of singularity at 0. It is actually constant 0. Okay. If I say -1, this is how the solution looks. So it's not bad, but then the previous one which I showed you, let me get back to the previous one. Here this looks much better. Okay, so this is how you can solve using numerically. Of course, you can write very easily. You can write a Python program for this. I don't have time, otherwise I would have just showed you. You can even solve system of OD. So for example, if I look at this system, I have x dash t is equal to x plus y, y dash t is equal to minus 2x plus y. This is first order system of ODE. How do I solve this? So I will declare first x as a function of t, y as a function of t. The first differential equation is dx by dt is equal to x plus y. Second is dy by dt is equal to minus 2x plus y. And then I'm creating the list of the first order, first equation and second equation, and using DE solve underscore system differential equation and x plus with respect to x and y. X and y are here dependent variables. Okay, and when we solve this, just 1 second. When we solve this is how the solution looks like. Xt is equal to half square root of 2 into sine square root 2t into y0. So this is initial conditions are not given, and so on. I can find out its left hand side, and I can find out the solution in terms of x and y. And we can even, or if I want to take the initial condition, for example, at 0, x0 is 0.55 and y0 is 0.1. And then when we try to solve, the solution will look like this. Now the constants are gone, and I can even plot this parametrically. So this is how the solution curves looks like. Implicitly, this is how it is defined. This is the solution. Let us try to plot, for example, this in terms of the slope field, and see how the graph looks like. So this is how the slope field looks like, and then this is the solution. This is how you can see here. X at t is around 0.55 and y at 0 is 0.1 something. Okay, so this is how the solution looks like, and this is the slope. You can also plot slope field about x-axis, about y-axis also can be plotted, but in this case both are linear, so it will look like a straight line. This is linear in x and y, so it will look like a straight line passing through origin. Okay, right. So here we have solved this analytically using DE solve, right? So it uses symbolic manipulations, but you can also solve using analytic solution. Similarly, the model which I showed you, for example, this earlier one in the beginning, one of them was SIR model, epidemic model. There is similar, very famous model called Lotka-Volterra model or predator and prey model. So, for example, if you look at in any environment, or look at any, for example, forest. For example, you can think of one as predator, one as prey. For example, rabbit and mouse, right? Or rabbit and foxes, not mouse, rabbit and foxes. So we know that foxes eat rabbit, right? So in order to both of them, if they have to survive, there is some kind of one can model this using this differential equation, and this again is a system of non-linear differential equation, right? So this also can be solved using. So here, what is x? X is the number of preys at time t. Y is number of predator at time t, and alpha, beta, gamma, delta are parameters. Alpha is called growth rate of prey. Beta is called the rate of shrinking of the one with respect to other, right? Gamma is shrinking rate of the predator population, and so on. And delta is the growth rate of predator. Okay, so you can solve this again using DE solve RK4 method. So here, if you want to solve this analytically, it may be slightly tedious. Of course, I don't think you have learned solving system of nonlinear equations, but you can solve using RK4 method. So RK4 method can be used for solving one equation or system of equations, both linear and non-linear. So if let me copy this again here, and we can solve this. So I have solved this numerically, and every point we have, and let us now try to plot how it looks like. So you can see here, this is how the solution looks like. The solution now you can see here, this red one is actually, think of this as rabbit, and the blue one is, let us say, foxes. So if the population of rabbit grows, the population of foxes also grows, and so on. So that is how you can, or you can even plot the interaction plot. This is how it looks like. This is the interaction plot. Okay. So let me copy. Right. Similarly, you can actually also solve using Laplace transform. That also you must have done. You can find Laplace transform of a function. You can find inverse Laplace transform. You can solve using Laplace transform. So let us see. For example, if I have t to the power n, where n is equal to 6, and if I want f dot Laplace t comma s, so it is 5 factorial divided by s to the power 7, right? That's the Laplace transform. Similarly, if I take n is equal to half, that means t to the power half Laplace transform, that is given by half into square, half times square root of pi into s to the power 3 by 2. Or I can put it in terms of alpha also. Assume alpha to be positive, t to the power alpha, its Laplace transform is s to the power minus 1 minus alpha into, so this is gamma of alpha plus 1. So this is actually gamma of alpha plus 1 divided by s to the power alpha plus 1. That is what it means. Okay. Where gamma function, you know that, is given by 0 to infinity, integral 0 to infinity e to the power alpha minus 1 e to the power minus t. So, or you can find out Laplace transform of sine a alpha. You can find out alpha Laplace transform of e to the power minus t squared into 2t. That is somewhat complicated. If you want to find it using integral, it will be not that easy, but Sage can find out. Of course, it is given in terms of error function. You may not have learned. So even for complicated function, it can find Laplace transform. You can even find Laplace transform of the derivative. If I have derivative of the function, and if I want to find out Laplace transform, you know that it is s into Laplace transform of ft minus f at 0. If I have second order derivative, then find the Laplace transform. It is s square into Laplace of ft into Laplace of ft into s into f at 0 minus derivative of f at 0, right? Or third derivative, right? So in general, this is how the Laplace transform of nth derivative. You can also find out inverse Laplace transform. So inverse Laplace transform of 1 upon s plus a is going to be e to the power minus at. Or inverse Laplace transform of 2s plus 3 divided by s square plus 3s plus 5 is going to be cos of cos of half into square root of 11 t divided by e to the power minus t. Right? So, and let us look at, for example, if I have this differential equation, dx by dt is equal, plus x is equal to cos 2t, x at 0 is equal to 0. And if I want to solve using Laplace transform, you can use a function called dsolve underscore Laplace and give the differential equation and give the initial condition. This is how you can solve. Right? Let me again put it in the chart. Yeah. Or you can even solve this is the same thing. You can even solve system of ODE. So you have here x dash equal to 1 minus y, y dash equal to 1 minus x. But here directly you don't have inbuilt function. So you may have to do a little bit of work. So I'm declaring capital X and capital Y. So capital X will replace Laplace transform of x, small x. Capital Y will replace with Y. So you can actually do step by step, and then. So here is also, for example, opportunity for you to write your own program and maybe contribute to SageMath of solving system of ODE using Laplace transform. There is no inbuilt function at present. So you can write very easily your own. I have given you a little bit this here. So something similar can be done in general, and you can write your own program. Okay, since all of you know Python programming, and also So here we have done step by step. Okay. Last one, let me also tell you, you can also plot Fourier series. So you already know what is the Fourier series, right? So if I have a function f, which is a periodic function with period 2 pi, and it is piecewise continuous in minus L to L, right? Then the Fourier series is given by this, where they are called Fourier coefficients, an and bn, right? These are given by this. So you can very easily find out. For example, let us look at this function. F of x equal to -1 when x lies between minus pi and 0, equal to 2 between 0 to pi by 2, and 1 between pi by 2 to 1. If you try to plot graph of this function in, I think this plot, yeah, this is how the graph of this function looks like. Okay. So how do we, let me copy this for you. So in case you want to, this is how the graph looks like. Now you can find out Fourier series cosine coefficient and fifth cosine coefficient. This is how it looks like. So there is inbuilt function to find, but you can also define integral. In terms of integral, you can very easily do. You'll get the same answer. Similarly, cosine coefficient we can find out. Fifth cosine coefficient, this is 1 upon pi. Here this is 1 upon 5 pi. And we can even find out Fourier series partial sums. So for in this first 5 term, we can find out, and this case, the 5 term, let us find out. This is how it looks like. This is the first 5 terms, right? So let me copy this. But let us also plot this function along with first 5 term. This is how it looks like, right? So you can see here it is, this is how it looks like. It is not a very good approximation, but as we take more and more terms in partial sums, the approximation will become much better, right? So let me copy this. So if I look at now, earlier it was 5 terms. Here, if I'm looking at 10 terms, this is becoming slightly better. Of course, this is still not very good. If I'm taking 20 terms in the partial sums, now you can see here. So Taylor series expansion is a kind of approximation using polynomial, but here it is polynomial is in some sense it's a polynomial in cosine and sine, because the function is periodic, right? So that is what it looks like. Similarly, if I take 50 term, then you can see here now it is much better approximation. Of course, there are varies quite a few, but if I take 100 terms, it will be even better, right? Now you can see here. So that is, so always dealing with sine and cosine function is much easier, right? And you have seen the applications of Fourier transforms, etc. So this is also can be thought of as series expansion, series involving sine and cosine, and geometrically this is how it looks like. This is how it happens. Okay, so these are the you can also, but here at present there is no inbuilt function to find Fourier transform, but using definition you can very easily, for standard function you can find out using integral, because the Sage also allows you indefinite integral, but uh, you can create, in fact, subroutine, Sage subroutine for Fourier transform and contribute to the development of Sage. Okay, since all of you are going to be computer science engineer, I think that is, so there are a lot of opportunity, not just using SageMath, but you can contribute in its development and get your name in the, as one of the developer also. You can think of that as a good project. Okay, since you have learned. So these are some of the reference. The website is best reference. Of course, on the website, there is also a book called Computational Mathematics with SageMath by Paul Zimmerman that you can download easily. And there is an NPTEL course by Hello, am I audible?
Yes, sir. Yes, sir.
Yeah. Sorry, I think that this is the problem. Okay, so course also by me on NPTEL called Computational Mathematics with SageMath that deals with calculus, linear algebra, which next semester you are going to learn. It also has some differential equation. It also has many other things, etc. And but there is also book, online book on ordinary differential equation using SageMath by Judson. So this website also you can look at. And in fact, one of the faculty from VIT Chennai has also contributed in this. He has written a paper on solving non-linear differential equation using a domain decomposition method using SageMath. So, but that it doesn't have inbuilt function, but he has written a paper on that. Of course, it is not part of the SageMath, but there are many opportunity. It can be possibly made into part of this. So I thought I'll just mention this. So it is SageMath is not just used in teaching, learning mathematics, but it's also used in research. I think let me stop. Thank you very much. I will be to take it.
Thank you, sir, for the wonderful lecture. Students, you can ask if you have any question. Sir will be happy to answer it.
It was slightly fast, but I will share this worksheet with all of you and you can use. Yeah, please go ahead if you have some questions.
I think students will look into it later.
There's no question? Okay. Yeah,
Thank you, sir.
no problem.
So I would like to express my sincere gratitude on the behalf of VIT Chennai Department of Mathematics to our esteemed guest speaker, Dr. Ajit Kumar, Head and Professor, ICT Mumbai. Thank you, sir. It was very relevant to the course, differential equation and transform. You explained very nicely the existence, uniqueness part. And so, thank you, sir. And the introduction to SageMath was really very interesting. And it is also new to me as well. I was not familiar with the software. So, uh, it's certainly it will be useful to the students as well. With this, uh, those who don't even know about the Python much, they can also start things. It's really interesting. Thank you, sir. I'm sure the students will
Thank you very
look more into it. Thank you so much, sir. And also, I would
Okay.
like to thank Mr. Nihar Rajan, one of our students, for preparing the guest lecture posters. Thank you, sir.
Thank you.
I will share the
Okay.
video also as you requested.
Sure. Okay. Thanks a lot. And
Thank you.
bye, all of you, and all the best.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Sir, I'll end the meeting.